Welcome to chapter 25. In this chapter, we're going to be looking at the relationship between electric fields and potential energy. So let's remind ourselves about potential energy. Now remember, potential energy is stored energy, energy due to position or arrangement. Potential energy is associated with conservative forces. And conservative forces, it turns out, except for spring, are linked to fields. So since electric charge can create an electric field, there is an associated conservative force with it, the electric force, and that force is associated with potential energy. Okay? Now, when there is a conservative force, kinetic energy is going to be converted to potential energy, or potential energy is going to be converted to kinetic energy without changing the total energy of the system. The work done by a conservative force is independent of the pathway between a point A and a point B. Okay? So, for example, if we were to lift a ball off the floor, the energy we are putting in goes in. We put energy in, it makes the ball move, we move it against gravity, the kinetic energy that that the ball has is being converted to potential energy. If we were to let go of the ball, then the potential energy of the ball would be converted to kinetic energy, and the internal energy of the ball would remain constant until it makes contact with the ground. Okay? This happens because the ball is interacting with the earth through a gravitational field. Okay, now let's just kind of remind ourselves about a few things. It's not been that long since we talked about work. Okay, but work, remember, is equal to the vector F dot vector delta S. And if we are dealing with a constant force, then it's F delta S cosine theta, where theta is the integral in between the two. Okay? So remember, this distance inside the bracket here is the portion of the distance traveled parallel to the force being applied. Okay? And if we're not dealing with a constant force, then of course we've got work is equal to the integral of F dot ds. So, if we're going to drag a box, let's say across a floor, with a 5 Newton force that makes an angle of 30 degrees with the horizontal for 5 meters, then we could calculate the work. Okay? Work here. Let's go over so we can see very quickly. Okay, work, maybe I need to use a black pen so it shows up a little better. Work would be the force, it's a 5 Newton force, times the distance, and I said that it was going 5 meters, and the force and the delta S have an angle of 30 degrees between them, so it'd be cosine of 30. So it would be 5 times 5 is 25 times the cosine of 30. So it'd be 21.7 joules. So, charged particles interact through fields, just like objects with mass interact with the Earth's gravitational field. So the Earth has mass, objects have mass, they work through a gravitational field. That means that electric forces are conservative forces, and work done by a conservative force does not change the mechanical energy of the system. Therefore, we see an electrical potential energy associated with a test charge in an electric field, just like we would see a gravitational potential energy for an object that had mass in the Earth's gravitational field. So, in this chapter we have some goals. To be able to calculate electrical potential energy, to be able to understand the motion of charged particles in an electric field by looking at the charged particle's electrical potential energy, and being able to understand how an electrical circuit works. Now, we're going to concentrate in on uniform electric fields, okay, like we would find between the plates of a parallel plate capacitor. We do this because the forces on the chest charge in this region of space would be constant. Okay? So, if I have parallel plate capacitors, and notice that the positive plate is over here, the negative plate is over here, the electric field lines then point from positive plate to negative plate, and that a positive test charge is going to experience a force in the direction of the electric field. So it's going to experience a force directed from the positive plate toward the negative plate. Okay? And if it moved a distance delta r, then we could say that work was being done by the force, and there would be a decrease in potential energy and an increase in kinetic energy. Okay, the book refers to this as falling in the direction of E, the electric field. So let's say some point, a 0 point. By tradition, the 0 point of our S-axis in this situation is considered to be the negative plate. So that's why the negative plate was put over here, because we're used to the positive direction being to the right. Okay? So positive S is toward the positive plate. Now, we see that the electric field points from positive plate to negative plate. We know the positive particle moves from positive plate to negative plate. So the particle is moving in the negative S direction. Okay? So as it moves in the negative S direction, we have an increase in potential energy. Come on. Guys, I'm working on getting the hang of this. Okay? So as it moves from the positive plate to the negative plate, we see an increase in kinetic energy, a decrease in potential energy. So the work electric is F dot ds. So F delta S cosine of theta. Okay? And we get Q is, we get the force is Q times minus E. Okay? And we have S final minus S initial. So we get Q E S initial minus Q E S final. Now, we're taking the cosine of 0 because delta S and F were pointing in the same direction. Okay, in our picture up here. Oh, I need to erase that. Erase. Okay, now just remember, okay, our force was in this direction, our delta R was in this direction, or delta S. They're parallel to each other, both pointing in the same direction. That's why the angle was 0. Come on. So as a particle moves from the positive particle moves from the positive plate toward the negative plate, the potential energy goes down, the kinetic energy goes up. it should be speeding up. And remember that work is equal to change in kinetic energy, which is negative the change in potential energy. Okay? If a negative particle were moving this from the same initial position to the same final position, what would happen? Now remember, the force on a negative particle is in the opposite direction as the electric field. And since it's in the negative of the direction of the electric field, the electric charge, the negative electric charge, charged particle would actually be slowing down because it'd be moving toward the negative plate. So its potential energy would actually go up. So the electrical potential energy would have to go up because the force on the negative particle is pointing in the opposite direction from the electric field vector and in the opposite direction from which the particle is traveling. So the negative particle is slowing down as it moves toward the negative plate. Okay? The electrical potential of a point charge in a uniform electric field is thought of as the following. Electrical potential energy is equal to the electrical potential energy at a point 0, S equals 0, plus QE times S. Now, by convention, we usually make the electrical 0 at point 0 to be the potential at the negative plate, and we usually think of this point as being 0. Remember, with gravitational potential energy, we usually choose, where you choose your 0 potential energy is up to you. Same thing here. Where we make our 0 electrical potential energy is up to us. And by convention, that's usually assigned to the negative plate where we make S equals 0. Okay? For a positive point charge, then, the electrical potential is going to be greatest near the positive plate and 0 at the negative plate. And for a negative charge, we'd expect it to be our greatest at the negative plate, and we'd actually expect it to, and if we make the negative plate 0, we'd expect the electrical potential at the positive plate to be negative. Okay, so for a point charge in a uniform electric field, the change in potential energy is the negative of the work electric, which is the negative of the change in kinetic energy, which is minus QE S initial minus QE S final. So let's do the calculation for a +1 nanocoulomb point charge moving an electric field of strength 500 newtons per coulomb, moving from S equals 0.1 centimeters to S equals 0.25 centimeters. Okay? Now, let's draw a picture, and then let's do the problem. Okay. Now, we've got parallel plate capacitor here. Our negative plate, our positive plate. Okay, so that means that the electric field points from the positive to the negative. Okay, and that our test charge is a positive test charge, and Q positive is equal +1 times 10 to the minus 9 coulombs. And it's moving from a position here, S equals 0.1 centimeters to S equals 0.25 centimeters. So it starts here, okay? velocity initially is in this direction. Now, what I want to do is I want to calculate, let's calculate the change in potential energy. Okay? It's going to be the negative of Q, which is 1 times 10 to the minus 9 coulombs, times the electric field strength, which I told you was 500 newtons per coulomb, times the strength, the initial position, which is 1 times 10 to the minus 3 meters, minus the 1 times 10 to the minus 9 coulombs, times 500 newtons per coulomb, times 2.5 times 10 to the minus 3 meters. So let's do the calculation. So 1 exp9 negative times 500 times 1 exp3 negative. So I have the negative of coulombs divide out, and I have newtons, meters, that's a joule. So I have 5 times 10 to the minus 10 joules minus 1 exp9 negative times 500 times 2.5 exp3 negative. So that's 1.25 times 10 to the minus 9 joules. Negative plus 5 exp10 negative. So I have the negative of a negative 7.5 times 10 to the minus 10 joules. So 0.25 exp9 negative. So the negative and negative cancel out. I get a positive 7.5 times 10 to the minus 10 joules. Okay? That means we have an increase in potential energy. Okay? Now that makes good sense, because I went from closer to the negative plate to closer to the positive plate. That means that V final here, when I get to this point, is going to be less than V initial. Because if the potential energy went up, that means that the kinetic energy had to go down. Okay. Traveling again. All right. Now, anytime I have 2 point charges, okay, they each create an electric field and they interact to each other with an electric field. So when I have 2 point charges, there's got to be a potential energy associated with how they're positioned relative to each other. So if I have 2 point charges, the potential energy between the 2 point charges, it turns out, equals K, Q1, Q2 over R. Notice it's not over R squared, it's over R. So the further apart those particles are, the lower their potential energy. The closer together they are, the higher the potential energy. Okay? So the 0 point for potential energy when we're dealing with point charges, 2 point charges interacting, is the 0 point is going to be at r equals infinity. So r is going to be 0 at infinity, and if they are both positive charges, when I bring them in very close together, they're going to have a very high potential energy. Okay? If I have two negative point charges and I bring them in close together, they're going to have a high potential energy. But if I bring a negative and a positive in close together, notice that if this is positive and this is negative, I get a potential energy that's negative. Okay? So the 0 point is going to be out at infinity, but the potential energy actually goes down as they approach each other. And the closer they get together, the lower their potential energy. The more negative the value of U is going to be. Now, for most cases, we're more interested in change in potential energy instead of in absolutes. So if I separate unlike charges, it requires an energy input because they were at a low potential energy, a negative value when they were in closer together, and as you move them further apart, it takes work, okay? It takes some external force to pull them there. Now for multiple point charges, you do the sum of the potentials for all of the combinations and all of their distances. We're not going to really worry about that too much. I just wanted to bring it up. We're not going to look at the potential of a dipole, so you can skip that little section. Now, let's think about a field that exists in a region of space, with or without a test charge to experience the force of that field. The field is there in that region of space, and the minute that a test charge enters that region of space, it's going to experience an electric force. That means that at every point in that region of space, there is the potential to create potential energy. Okay, I'm going to say that one more time. There is the potential to create potential energy. So the potential to create potential energy is there whether there's anything to experience it or not. So if you think about it kind of like a hill. A hill is there for somebody to roll down even if there isn't anybody there to roll down the hill. Okay? The ability to create electrical potential energy is called electrical potential. Okay? Let me say it one more time. The ability to create electrical potential energy is called electrical potential, and it's given the symbol V. V, electrical potential, is equal to electrical potential energy divided by QT, the test charge. U, electric, then, is equal to electrical potential times QT. Okay? The units on electrical potential are joules per coulomb, and we call that a volt. So electrical potential energy is equal to electrical potential times the test charge that is experiencing the electric field. Okay? Now, electrical potential is a lot like field. The field is there in a region of space for a particle to experience. When it moves into that region of space, it experiences an electric force. The electric force then is going to change its kinetic energy. When it changes its kinetic energy, there is a corresponding change in potential energy because it's going to move. Okay? So electrical potential is very much related to electric field. It's something that exists in a region of space that depends only on the source charge and not on what the test charge is, and it's there whether anything is there to experience it or not. So it exists in space even if nothing there to experience it. We can talk about electric potential independent of charges that can experience the electrical potential, experience the field. So electrical potential is just another way to talk about electric fields and disturbances in space. So we know if there's an electric field in a region of space, there's an electrical potential in the region of space, and we know that a test charge introduced to that region in space is going to have a electrical potential energy, okay, and it's going to experience an electric force. So let's do a language check. Okay, so we can talk about potential difference, and when a charged particle moves through a potential difference, it experiences a change in electrical potential energy, and therefore a change in kinetic energy. So remember, change in kinetic energy plus change in electrical potential energy would equal to a change in kinetic energy plus QT, the test charge, delta V. The test charge, remember, is whatever charge we have introduced into that region in space to experience the field. So we can say change in kinetic energy for the particle is equal to minus QT delta V. Because remember, when I moved this over, it became negative. So we're going to look at a couple of problems. We're going to look at problem 11 and we're going to look at problem 14, both on page 709. Okay, so there's both the problems. Let's look at these two. It says, what is the speed of a proton that is accelerated from rest through a potential difference of minus 1,000 volts? Get the board clean here so we have some room to work. Okay, guys. So, I've got our change in potential energy, potential difference, delta V is minus 1,000 volts. Change in kinetic energy is equal to negative QT delta V, and we were told that we have an electron. So the charge on an electron is minus 1.60 times 10 to the minus 19 coulombs. So I have the negative of a negative 1.60 times 10 to the minus 19 coulombs times a minus 1,000 volts. So the negative and negative here, I have three negatives, so I'm going to get a negative answer. So 1,000 times 1.60 exp 19 negative. So I end up with a minus 1.60 times 10 to the minus 6 joules. A coulomb times a volt is equal to a joule. So it's minus 1.60 times 10 to the minus 6 joules. Now, guys, let's think about this. Okay? The negative plate of a parallel plate capacitor, the positive plate of a parallel plate capacitor. Okay? Electric fields point in this direction. Turns out that electrical potential is highest at the positive point charge, it's lowest at the negative point charge. Electrical potential, okay, decreases as you move from positive to negative. So I have a negative electron here, and it's moving initially toward the negative plate. If it's moving toward the negative plate, okay, so this was 1000 volts, let's say this was 0 volts, okay, then if it's moving toward the negative plate, I'd expect its electrical potential energy to go down, and in this case, its electrical potential energy to go up and its kinetic energy to go down, because it's a negative particle moving toward the negative plate. Okay? Now, let's look at problem 14. We look at problem 14, it says, what potential difference is needed to accelerate a helium 1+ ion plus E charge mass 4U from rest to a speed of 2.0 times 10 to the 6 meters per second. Okay, so let's look at problem 14. All right, let's erase things here. Okay. Now, it says what potential difference do we need to do to take it from rest to 2.0 times 10 to the 6 meters per second. So here's going to be my initial point. Okay? Over here is going to be my final point. Velocity initially is 0. Velocity final is 2.0 times 10 to the 6 meters per second, and that's its magnitude. Okay? And we know that our charge Q is 1.60 times 10 to the minus 19 coulombs, and its mass, okay, is 4 AMUs, so let's see, 4 grams. We figure out the mass here real quick. So I have its mass is 6.64 times 10 to the minus 24 grams. So that's 6.64 times 10 to the minus 27 kilograms. Okay? So we know that the change in kinetic energy is going to be 1/2 times the mass, which is 6.64 times 10 to the minus 27 kilograms. The final squared, which is 2.0 times 10 to the 6 meters per second squared minus 0. So 2exp6 squared times 6.64 times 10 to the minus 27 divided by 2 gives us a change in kinetic energy of 1.33 times 10 to the minus 11. And that's in joules. So the kinetic energy is increased. The change in potential energy then is minus 1.33 times 10 to the minus 11 joules. And remember that the change in potential energy is equal to Q delta V. So I have a minus 1.33 times 10 to the minus 11 joules is equal to the test charge, which is minus 1.60 times 10 to the minus 19 coulombs times delta V. Oh, excuse me, that's a positive because it's a proton. Well, it's a positively charged particle. So 1.33 exp 11 negative divided by, so the change in potential is a minus 8.31 times 10 to the 7 volts. Now, I expected the potential to be negative because I went from a region of higher potential energy to a region of lower potential energy for a positive point charge. A decrease in potential energy as I move in that direction. Okay? So these are really kind of plug and chug problems. They're not too bad. I did throw an extra step in there, but you could have also said the change in kinetic energy is minus Q delta V, and you would have gotten the same thing. Okay? So, two ways you could have worked it. I threw in an extra step. Okay, let me erase this so that we're ready when we hit the next problem. All right, let's move back over here where we can see the screen. Okay, let me shut down here for a second. I need to change out my battery. Now let's move on and let's talk about the electrical potential between the plates of a parallel plate capacitor, and let's start relating the electric field to the strength of the electrical potential, okay, and eventually to voltage. So we know the strength of the electric field inside a parallel plate capacitor is equal to eta divided by epsilon 0, where eta, remember, is our surface charge, our charge per unit area, and epsilon 0 is a constant. The electrical potential at any point between the parallel plate capacitors is equal to Q test times E times S plus the potential at the 0 position, which we assign S equals 0 to the negative plate, normally, where U0 is going to be 0 if we're dealing with a positive test charge. Okay, so we usually assign U0 to be 0 at the negative plate. We say that the electrical potential is equal to Q test times E times S. Okay? All right. The electrical potential at a location S is measured from the negative plate, the parallel plate capacitor. Then V is equal to U electric over QT, or V is equal to E times S times QT divided by QT, or E times S. Strength of the electric field times our position from the negative plate, assuming that we have a zero potential at the negative plate. Okay? So that means the electrical potential, well, if the electrical potential is not zero at the negative plate, then we say that the potential at any point is equal to V0 plus ES. Okay? Where V0 is the electrical potential at the negative plate. So the potential difference between two plates of a parallel plate capacitor, okay, delta V, the potential across a parallel plate capacitor, is equal to V positive minus V negative, which is equal to the strength of the electric field times the D, the distance of separation between the plates. So if we increase the separation between the plates while keeping the strength of the electric field the same, if D goes up and E stays constant, then the electrical potential between the plates would go up because I increased the size of D. The electrical potential decreases then linearly as we move from the positive plate to the negative plate in a parallel plate capacitor. So it's highest here at the positive plate and it's lowest at its negative plate. Okay, it's a linear relationship. So if we look at the stop and think on page 698 in your text, in the middle of the page, okay guys, remember I gotta run across the room to do things. So we're looking at page 698. Let's look at the stop and think here. It says a proton is released from rest at point B, where the potential is 0. Afterwards, the proton will do what? So it's right here, and it's released from rest. Where will it go? Well, okay. Since it's in this region of space, we know it's experiencing an electric field, because from one side of it to the other, there are different electrical potentials. It is going to experience a force in the direction of the electric field lines, and electric fields always point from higher potential to lower potential. So a positive proton put right here is going to move in this direction to decreasing electrical potential if it's released from released from rest. Now, in this region of space, it's experiencing a continuous force, okay? And it's a constant force. So if it's experiencing a constant force in this region of space, it's going to speed up. So it's going to move toward A with an increasing speed. Okay? It's not going to remain at rest because it's experiencing a electric field, so an electric force. If it's experiencing a constant force, then it can't be moving at a steady speed. Remember, the net force has to be 0 for something to move at a steady speed. And it's always going to move in the direction of the electric field, which points from higher electrical potential toward lower electrical potential. So V, the electrical potential, is equal to E times S, where S delta V of the capacitor divided by D, the separation of the capacitor. So, got rid of that. Okay, get rid of that. Let's get this back down here where I want it. Boy, it jumped way down there. Okay, we're right here. Okay, guys. We have a parallel plate capacitor here. And we say that this plate is at 1.5 volts and this one is at 0 volts. The dotted lines here are what are referred to as equal potential surfaces. Remember earlier I told you that the electrical potential decreases linearly from the positive plate to the negative plate. So when we look at equal potential surfaces for the region inside a parallel plate capacitor, they're always going to be evenly spaced. Okay? So if I look at the difference here and here, they said this is 3 millimeters. 1.5 divided by 3 millimeters means that it's going to be 0.5 at 1 millimeter. It's going to be 1 at 2 millimeters and 1.5 at 3 millimeters. So they're equal potential surfaces. Okay? Now, the delta V capacitor for this whole capacitor is 1.5 volts. So if I took 1.5 volts divided by the 3 millimeters, okay, multiplied by the distance from this plate, I would get the potential at any location between the plates. Now, equal potential surface. An equal potential surface is a surface along which the electrical potential is always the same. Okay? So the dots up above, the dotted lines up above, or those green plates in the last diagram were equal potential surfaces. If you move along an equal potential surface, there's no change in potential energy for a charged particle, and there would be no change in speed because they're not experiencing any kind of net force. Okay? Electric field lines are always perpendicular to equal potential surfaces, and point in the direction of decreasing electrical potential. So if we're looking at the plates of a parallel plate capacitor, it points towards the negative plate. Okay? So let's look at problem 19 on page 709. Problem 19, it says the student wants to make a very small particle accelerator using a 9-volt battery. What speed will a proton and an electron have after being accelerated from rest through a 9-volt potential difference? Okay? So, let's start looking at things. Okay. So this is 9 volts, this is 0 volts. Okay? And we're going to start out with a proton. The mass of a proton is something that I should have memorized, but at the moment it's slipping my mind.